In this video, I talk about the solution of nonlinear equations, both algebraic and transcendental equations. Let's put a breakpoint in line 3 and let's run the script. We start with defining a symbolic variable, let's call it x, and let's try to solve a simple quadratic equation, an equation of degree 2, by the function solve. Please note that if there is a term like this one as the argument of solve, it's assumed that the equation to be solved is this term equals 0. So effectively we look for the zeros of the polynomial x squared plus 5x minus 17. This polynomial has two solutions. The result are two symbolic constants, as you can see here. They are of class sym, but we can convert them to numerical values by the function double. So these are the two solutions of this simple quadratic equation. We can also ask directly for numerical values by invoking the function VPA solve. And here we get these two symbolic constants with 32 significant digits. We can again convert those to numerical values, but then we are left with only about 15 to 16 significant digits. We can also solve equation polynomial of degree 3, the third order equation. In this case, we get three solutions, two of which are complex numbers. We can ask only for the real solutions by giving the parameter real the logical value true. So in this case, we get only one, the single real solution of this equation of degree 3. You probably know that there are explicit formulas for algebraic equations only up to degree 4. So if we try to solve an equation of degree 5, we don't get any useful results. In this case, it makes better sense to directly invoke VPA solve. This will return the 5 solutions, one of which is real, and the other ones are two pairs of conjugate complex numbers. This can then be converted to numerical values by the function double, wrong window. Okay, so these are now the numerical solutions, and they are of type double with the attribute complex. Now let's pass to single transcendental equations, equations involving transcendental functions like the trigonometric functions or the exponential function. Let's try first the simple equation sine of x equals 1. You can see that it's possible to add an argument that indicates with respect to which variable the equation has to be solved. In this case, it's redundant because there is only a single variable in the equation, namely x. So this gives one solution of the equation sine x equals 1, which is pi over 2. But you know that, in fact, this equation has an infinite number of solutions, and we can get those in a parameterized form by giving the parameter return conditions the logical value true. So if we execute this call to the function solve, we get a parameterized form of the solution. It's pi over 2 plus 2 times pi times k. K is a parameter, and the condition on this parameter is that it's an integer. So all solutions are pi over 2 plus an integer multiple of pi. We can play the same game for these equations. Sine of 2x equals 0.5. We get again a parameterized solution of this form, either pi over 12 plus pi times k, or 5 times pi over 12 plus pi times k. K is a parameter, and it's again an integer. Another example, sine of x over 2 equals 0.25. This gives this parameterized solution. The next equation involves the exponential functions. We ask for solutions to the equation x times e to the x equals 10. And again, we ask for a parameterized form so that we can get all possible solutions. This gives the following result. The general solution is expressed in terms of Lambert's W function. Please look it up in Wikipedia if you don't know about it. It has a parameter k. The parameter k corresponds to the branch of the function, and k is again an integer. We can evaluate this function. So if k equals 0, the principal branch of the function, we get, sorry, forgot the w, we get a real solution about 1.745. And the other branches, we get complex solutions. Of course, there are infinitely many branches of this function. Now let's try a similar equation. X times sine of x equals 0.6. In this case, there is no general parametric solution, but there is of course an infinity of solutions, but they cannot be easily parameterized by using a higher function like Lambert's W function. If we execute line 21, we do get a solution, but maybe not the solution that we're interested in. We get the first solution that the function solve finds, which in this case is minus 2 to 6.2 approximately. But we can try to find zeros with different starting points. For instance, we can instruct VPA solve to find a solution with starting point 2, and it finds 0.82. Let's try a different starting point, let's say 5, and we get a different solution. We can try minus 2 and minus 5. So in this case, it makes sense to give a starting point if one wants to find a solution in a certain area, a certain vicinity on the real number line. Next, we look at the problem of the solution of several algebraic equations. For instance, if you want to find the intersection points of two algebraic curves, you have to solve two algebraic equations jointly. This can also be parameterized by constants, in this case symbolic constants a and b. So you will recognize the first argument of solve in line 30 as the equation of an ellipse. The second argument is a line, and we solve these two equations with respect to x and y. So we find intersection points of this ellipse with a straight line. We store the result in the structure, in the output argument sol, it's a structure, and sol.x contains the x values of the two solutions, and sol.y contains the y values. Of course, this is not restricted to algebraic equations. We can, for instance, try to find the point of intersection of this circle, the unit circle, and the sine function. There is no symbolic solution for this problem, so we use VPA solve to find numerical solutions, and we see that the x value of the point of intersection of the unit circle with the sine function is this value, and the y coordinate of the intersection point is this value.